Hey guys, how you guys doing?
Hey, what's up, fellas?
Yeah,
You guys ready?
You know it.
Got your
as I'll
wingsuits
ever
on?
be.
I wish I had a wingsuit.
Yeah. You're gonna feel like you have one now. Okay, so
Oh,
let's go. So what we want to do here is that we want to look at examples here. We have 2 examples to do before the end of today, and I'm planning on having our first our quiz on this, and you're gonna get 2 problems, one with the constant source and one with the time-dependent source. So you could just say that this is a mini exam. So that will be on Monday, and I'm going to give you extra time as a result of that. So here's what we're looking at. We had this circuit, and one of the things that we did here is that we know that when the switch is open, I include the 5 amp source, and then if I do a source transformation, I then have a 32 and a 30 volt source here that are opposing. So when I look at the inductor current, it does this. As soon as the switch is closed, I kill off that 5 amp source. In other words, I kill off that 30 volt source. So I only have the 32 volt source feeding this inductor. As a result, the inductor has to increase current. Therefore, it stores up the current. So what we want to do here is that we want to go in and we want to get the complete response. We're going to look for this 24 ohm resistor, which is, you can see is in series with the inductor. So therefore, we expect no discontinuity in the 24 ohm resistor. So let's go through the process then. Okay, here we go. So what we're going to do here is that let's write out the 4-step process. To determine the voltage of the 24 ohm resistor. Okay, so here we go. Step 1. What we're going to do here is that we need to derive the first order equation. And we need to check whether this first order equation makes any sense by looking at IL infinity. Then the next step that we want to do is that we want to go in and we want to derive the general response. And remember, when I say the general response, that means we write it with the constants. Okay, so we're going to derive the general response equation and determine the forcing constants. And I don't know how many there are, but I'm just going to assume that there's 2. There could be 1, 2, and 3, but or it could be 1. But I will always write B1 and B2. And then our next step here in 3 here is that now we solve for IC. In this case, it's going to be IL at 0 minus. We need to determine the integration constant, which I call A, and write out the complete response. IL of t. Now that we have IL of t, I go to step 4, which now I have to solve the circuit problem. For V24 ohm using IL of t. And then we always then go and plot V24 versus T and interpret. So what you want to do here is that you want to get into a rhythm, right? Sort of like get a sense of what is going on and follow that rhythm. Derive the first order equation, check it to make sure that it works. Second of all, get that general response equation. So that means there's two things. You got to pick off the tau. Then you got to go in and you got to go determine the forcing constants. Once you have that, then go get the IC so you could solve for the constant A, write out the solutions for IL. And then finally, solve the circuit problem. So here we go. Let's go do the circuit here. So the circuit that we have here looks something like this here. So if I look at that circuit, here's my circuit. So you could see that when t equals to 0 plus, this exponential source turns on. So I have two sources in the circuit now. I have the 32 volt and the 8e to the minus 5t. Everything else over here is gone. So let's go write that. So here's our first step here. Derive first order equation and check it. So if I look at my circuit, what does my circuit look like? Well, I have an exponential source, which is 8e to the minus 5t. Then I have a resistor and an inductor. And then I have my second source, which is this 32 volt source. So I have my 24 ohm, I have my 8 Henry, and that's my circuit right there. So the first thing that I got to do here is that I got to write an equation that's going to do what? I have to write an equation that's going to connect IL and VL. So that means here is that I need to write an equation that contains IL and VLT. And you could see that because this is series, implies that you want to use KVL. So I'm going to use KVL. So I'm going to go all the way around. So if I go all the way around, note that because they're in series here, you could see that the current in this circuit here is IL. So if I do that, then here I go. So then KVL tells me that it's got to be this. So if I start at the inductor, you could see that the polarity of these guys should be exactly like this. So if I do that, then here I go. So it's going to be VL. Then I'm going to go around here, and I'm going to get minus 32 minus 8e to the minus 5t, and then I'm going to get plus the voltage of the 24 ohm resistor, which should be 24 IL equal to 0. So in other words, I now have my VL and my IL connected. So what I'm going to do next here is I'm going to replace VL with L di dt. So note that L is 8. So if I plug that guy into here, this is the equation that I'm going to get. I'm going to isolate di dt. Now note I have an 8 in here. So what I'm going to do, I'm going to divide everything by 8. So I'm going to get 32 turns into 4. 8 turns into 1. 24 turns into 3. So then I'm going to get 3IL. Then I'm going to take those guys to the other side. So I'm going to get, so if I look at the 8, that's going to be a 1. If I look at the 32, that's going to be a 4. So I should get 4 plus e to the minus 5t. There's my first order equation right there. Now, the thing that I want to do here is that I want to do a simple check. So now we want to do a simple check. to see if it behaves correctly for t equal to infinity. Now look at this source here. What you're seeing here is that I know that at steady state, at t equal to infinity, the inductor current must equal to a constant. So when I look at this thing, you could see here that then I'm going to have di dt plus 3il. I'm then going to say that I is going to be a constant. So what you're seeing here is that that constant is going to be, of course, it's going to be 0 when I take the derivative of it. Then I'm going to get 3 times a constant. You know what? I'm going to change how I write this. I need to make this a little bit better. So IL is then going to be I at infinity. So this is going to be IL at infinity. And then my source here should be 4 plus e to minus infinity, which is, of course, 0. My differential equation then tells me here is that IL at infinity should be 4/3 amps. Okay, that's what this guy's telling me. So what I want to do now is that, does this make physical sense? What I do now is that I look at the circuit at t equal to infinity. So let's go look at the circuit. At t equal to infinity, what do I find? I find that the exponential source has gone to 0. My inductor has become a short. So when I look at the circuit here, I'm seeing that I have this. My inductor now is a short, and I only have a 32 volt source here. So this current right here is IL at infinity. So what is this thing here? Well, we can see here is that the current of the inductor at infinity must be the current of the 24 ohm resistor at infinity, which is, of course, has to be 32 volts divided by 24 ohms. And you could see here that that gives me 4/3 amp. So what that tells me here is that these two guys, they match up. So it's a simple check. That doesn't mean that you're guaranteed a correct equation, but it tells you that at least you've gone through the first check. Let's go to the second step. So step 2. So now that I have step 2 here, what I'm going to do here is that I'm going to derive the general response and determine the forcing constants. So let's go do that. So I look at my equation. Here's my equation. So my first order equation reads what? di dt plus 3il equals 4 plus e to the minus 5t. So when I look at this thing, the first thing that I want to do here is that I know that that when I look at the solution here, right, my solution, my general response solution should be of the form IL of t is going to be a e to the minus t over tau plus, look at this guy here. Look at this guy. This guy is a constant. This guy here is exponential. So by looking at the effective source, my forcing response must be the same functional form as the right side. Therefore, I should have a term that reads B1, which will be a constant, and then B2, which will be e to the minus 5t. So this guy is what? Has the same functional form as the effective source. Now this guy, what I got to do here is that I have to pick off the 1 over tau term. And so what you're seeing here is that the tau is the cofactor of IL. So what this tells me immediately is it tells me this here. So what I'm going to do here is that I got to pick off 1 over tau, where that second term, remember, looks like this here. So what that means here, that this tells me here, is that 3 must be 1 over tau. So of course, I now have what that equation looks like. So my general response now, so I should be careful here. I should be highlighting this guy. So I'm getting my general response here. Okay, so my overall general response is then going to be IL of t. It's going to be a e to the minus 3t plus b1 plus b2 e to the minus 5t. So I now have my general response. And so just to make sure, where my forced response is really b1 plus b2 e to the minus 5t. So now what I got to do here is that I got to determine constants b1 and b2. Okay, so now that I have my constants b1 and b2, how do I do that? I'm going to substitute my forced response into my differential equation. Okay, so now what we do here is that we sub the force response into the first order equation. So let's do that. So here I go. So I have dIF dt plus 3IF, where I'm going to do what? IF is then going to be B1, B2, e to the minus 5t. Let's substitute that. So if I take the first derivative of this guy, note that B1 disappears, but then I'm going to get a term that's going to read what? Minus 5B2 e to the minus 5t. And then I get my second term, which would be 3 times B1, B2 e to the minus 5t. And then the right hand of this thing here, we're forcing these to match the solution. And that differential equation should be 4 plus e to the minus 5t. So you could see that I have an equation that has exponentials and constants. So if I look at this guy, look what I'm seeing. I have an exponential term here, here, here. I have a constant term here and here. So I got to match up the reds and the greens. So what this gives me here is that this gives me 2 equations and 2 unknowns. So here I go. So I'm going to get the B1 equation. So if I look at the B1, it's talking about the green ones. So you could see here that I have to have what? 3B1 has to equal 4. So therefore, B1 has to be 4/3 amp. I now know one of the constants. Then let's look at the B2 term. the B2 term, you could see here is that I'm going to get what? I'm going to get minus, oh, I said B2 terms. I really should say the e to the minus 5t terms is what I'm looking for. So I'm going to get minus 5 B2. Look at the second term. I'm going to get plus 3 B2, and that has to equal what? 1, where this whole thing is multiplied by e to the minus 5t. So what you're seeing here is that I have one equation for B2. And so this tells me here that now I can solve for B2. And if you look at this, this is going to be minus B2 equal to 1. So therefore, this implies here is that B2 must be minus 1/2. I now have my constants, my forcing constants. So now the general response equation looks like IL of t. This will be a e to the minus 3t. And then I'm going to put in my constants here. If I put in my constants, you could see this is going to be 4/3 minus 1/2 e to the minus 5t. So now I have my equation. So now I'm going to go to what? I'm going to go to the next piece. So now what I got to do here is that I got to solve for the initial condition here. So let's go do that. So here I go, step 3. What I'm going to do here is I'm going to solve for IL of 0 minus, determine the A constant, and write out the complete response. So let's go do that. So the first thing that I got to do here is I got to go get my circuit. And this is the circuit at t equals to 0 minus. So when I look at that circuit here, let me go get that circuit because I need that just to make sure that we're all clear on this thing here. What am I seeing here? What I'm finding here is that this is my circuit right here. And you can see that at t equal to 0 minus, I don't have this source right here, right? This is gone. I have the inductor, which is now what? A short, and I have the 5 amp source. So my circuit really looks something like this here. It should give me something that looks like this here. So I have my 24, then my inductor is a short, and then I have my 32 volt source. And I know that this guy, from what we've already talked about, this guy was IL of 0 minus. And then what we did here is that right in here, we did a source transformation. And I think I'm going to continue to do that. So if I do a source transformation, what I really have here is that I have a 6, and then I have a 30 volt source here. And this guy's a 6 ohm. So you could see here is that I'm just going to use Ohm's law to get this. Right? So according to Ohm's law, shows us that the current of the inductor is then going to be the voltage in the circuit, which of course is 32 minus 30 volts. And then I got to sum these guys, which will be 24 plus 6. So I get 2 over 30, which then gives me a 15th of an amp. But of course, we know that this is at 0 plus also. And we're only interested at 0 plus because that's the circuit that we solved. So now I have my initial condition. So the next thing that I'm going to do here is that I'm going to apply this to the general response. So here I go. So I got IL of 0 plus. That is going to be what? 1/15th. And that's going to equal what? A to e to the 0 plus 4/3 minus 1/2 e to the 0. So I have this equation right here. And then I just got to solve for A here. So then you could see here is that I got a series of things here. So then A is going to be what? 1/15th minus 4/3. So that should be 20/15. I don't know if that helped here. Plus 1/2. And if you compute this number, I'm going to get a value that reads minus 2330. And now I have my constant. So now that I have my constant, then that means here is that I can finally write the general response. Or the complete response. The complete response of inductor is going to be IL of t. I got my A constant. So I could see that my solution looks like up here. I think I'm going to put the constant up in front. How am I going to write this? Well, I'm going to write my constant up in front. Then I have my A term, which will then be 2330 e to the minus 3t minus 1/2 e to the minus 5t. And of course, this has units of amps. So that's my complete response. So what I want to do here is that I want to go in and I now want to solve the circuit problem. And the circuit problem that we're talking about has to be what? It has to be the voltage of the 24 ohm resistor. So now we're at step 4. And step 4 here is that we're going to solve the circuit problem for V24 ohm of T. And when you look at the circuit and plot it, we want to solve for this. We want to plot it and interpret. So let's go do that. So what do I know? Well, let's go look at the circuit. Well, if we look at the circuit, you could see here that the 24 ohm and the 8 Henry inductor are in series, so they must have the same current. So since an 8 Henry inductor are in series, they have the same current. So that means that the voltage of the 24 ohm resistor then should be 24 times IL of T. So if I write this guy out, you could see here is that I got to multiply 24 times 4/3, right? So let's write this out. So I'm going to get 24 times 4 divided by 3. Then I'm going to get 24 times 23 divided by 30 and times e to the minus 3t. And then I'm going to get 24 times 1/2 e to the minus 5t. So if I look at this guy, what am I actually seeing? Well, I got 3 into 24 is 8, so I should have 32. Then I'm going to get a minus here, and then let's look at this guy here. So if I look at this guy, what does this number? Wow, this looks like an ugly number. Let's go to this other one. So this is 24 divided by 2, that's 12. So I'm going to write 12e to the minus 5t. You're not getting a lot of love on this problem right here, right? So this is 8 times 3, 3 times 10. So what is that? Let me go to my notes. Shit, I'm not going to try to calculate that thing. Okay, my notes say that it's 92/5. I hope that's right. Okay, so then this is V 24 ohm of T. That is our solution. We now have our solution. So now we want to go plot this thing. So assuming that our solution is correct, what we're seeing here is that this guy, what I'm going to see here is that the first thing that I would look at is that what is this guy at t equals to 0 here? Well, at t equal to 0 minus, which should be equal to 0 plus in this case, we should have the exact same thing. This at t equal to 0 minus, which should be the same as 0 plus, the voltage V24 of t should not have any discontinuity. And the reason why, of course, is because IL of 0 minus must be the same as IL at 0 plus. So what we got to do here is that we got to compute this guy, which then gives us, let's see, 92 divided by 5. I'm going to get a value of this. So that means here that V24 at 0 should be 32 minus 12 minus 92 divided by 5. And the value that I get here is 1.6. And then I'm seeing here is that V24 at t equal to infinity, we clearly have 32 volts. So when I'm looking at this guy, what I'm seeing here is that, look at the minus sign. The minus sign indicates again that we're getting charging, right? The inductor is storing current. So we could clearly see by this. So if I plot this, what should it look like? Well, if I have a curve, it should look something like this. So V24 of t, I'm going to see here is that this guy's coming in at what? This is V24 at 0 should be 1.6 volts. And then this guy is going to charge up or store current all the way up to V24 at infinity, which is 32 volts. So what I expect to happen here is that I would expect some type of RC behavior that looks something like this. So now we interpreted, we didn't expect any discontinuities because it was in series with the inductor. And now I see this RC behavior. Now remember what we said here, that we expected storing up of current. Why? Well, mathematically, we see here is that if we have a solution for an inductor, if I have a constant source, one of the things that we saw here is that we had this current like this here. And remember what we said, that if it stores current, we should have what? A minus sign right there. Look what we're looking at mathematically. I have two exponentials with minus signs, and therefore that tells us that it should be storing up current. So it makes physical sense from what we checked it with just looking at the solution by looking at what we expected. And then the second thing here is that we went in and we did it for sort of like looking at the steady state values to actually see what was going on. So here we go. Let's go to the next piece here. So what I'm going to do here, I got our second example that we want to look at. The fact that you see a dependent source in the circuit means that it's going to be more involved, right? Without any doubt. So let's go look at this circuit and try to interpret what's going on. So what do I expect from this circuit here? So clearly we have that dependent source, and if we have a dependent source, we have to have a dependent condition, a DC. So the question is, does the cap charge up or does it discharge? Well, for starters here, what we're seeing here is that at t equal to 0 minus, what happens? I have a circuit that looks like this. I have a 12 ohm. I have a dependent source. So this is 2Ix. Of course, I have a current Ix here. Note that the exponential source doesn't show up. So then I have a cap. And of course, that cap here has reached steady state. So this guy is then going to give me Vc of 0 minus. And then I have a source in the circuit. So what I'm seeing here is that I'm going to have a voltage because of that 38.5 volt source here. So I expect a value for that. Now, at t equal to 0 plus, what happens? You could see that that switch opens up. So when that switch opens up, look what I'm seeing here. I now have a source in the circuit. Now, again, here's my dependent condition, Ix. But now look at what's going on. I have an exponential source that's going to do what? It's going to be dying. So when I look at this guy here, what I'm seeing here is that when this guy goes to Vc at infinity, since that source is dying, I expect that the final voltage of the capacitor should be 0. In other words, this capacitor is discharging. So our solution must be a discharging cap. If it's not, we know we got a problem. So then I want to go through the same process. Okay. And what do I mean by go through the same process? I got to go in and I got to do what? I got to write out my process here. So once again, let's write it. And the reason why we're writing this out is to try to drive in the process into your head. So here we go. Here's our 4-step process here. So using our 4-step process. So here I go. Step 1. What do I got to do? I got to derive the first order equation. For VC and check it with our VC of infinity solution. They don't match. That means you derive your first order equation incorrectly. Go back and fix it. Step 2, what we want to do is that we need to derive the general response equation. And determine the forcing constants. And remember, there could be 3 of them, there could be 1 of them. I just typically write just B1, B2. Now I'm going to go to my next step. And my next step here is that I want to solve for the IC. So in this case, it's got to be VC of 0 minus. I need to determine the constant. And write out the complete response. VC of t. Now, when you look at the solution here, what you're finding here is that there is nothing that we're solving for. We're really solving for VC. So the last thing that we want to do here is that we want to go in and we want to plot VC of t and interpret. Okay, so let's go look at this thing here. So the first thing that I want to do here is that I want to go in and derive this thing. Okay, let's go derive this thing. So the first thing that I want to do here is that I got to get that circuit and I got to look at what happens at t equals to 0 plus. So here I go. So step 1, what I'm going to do here is I'm going to derive first order equation for t equals to 0 plus, right? So let's go look at the circuit. So what I'm seeing here for t equal to 0 plus, there is no 38.5 volt source. So I only have the circuit right in here. So let's go write that out. So if I go write that out, it's got to look like this here. So that means I have a 12 ohm. I have my current source. I see that this guy is 2Ix. Here is my dependent condition right there, Ix. Then I have my source, which is minus plus, and then I have my capacitor here. Okay, so I see that this is a 136 farad capacitor. Of course, we're looking for VC here. Now, my source here is, you know what, I'm going to bring this down a little bit. My source looks like this here. It's going to be 8e to the minus 5t volts, of course. So the first thing that I notice here is that I have a DC because I have a dependent current source. So there's this really a two-step process here. So we need a two-step process. First thing that I got to do is I got to write an equation to connect VC and IL. And then what I have here is that I need a DC condition. So that means I got to write, DC condition implies we must write IX either as a function of VC or IC. And look at that, I wrote IL, but I really meant IC here. So let me be careful here. So it's either got to be in terms of VC or IC. So the first thing that I'm seeing here is that how do I connect? Probably the easiest way to do this here is that I'm really setting up two equations and two unknowns. Actually, I have two equations and three unknowns. This is really two equations and three unknowns. And what I mean by that is that, of course, I need VC and IC to be connected, but now I have IX. I somehow have to connect that. And I think the easiest way to do this here is that I'm going to first, what I'm going to go after, typically I would go VC, IC first, but I think I'm going to use my DC first. And the reason why I'm going to do my DC first is check this out. Look at this node right here. Look how I have IX coming in, and then I have two IX, and you could immediately see here that I have IC moving in that direction. So let's write down our DC equation. So the first thing I'm going to write here is the DC equation. And I'm going to look at the purple node. So at purple node, apply KCL. And when I look at that thing, you could see here is that that tells me that I got to have IX plus 2IX, and that equals to IC. In other words, IC must be the same as 3IX. Boom. I've now written a DC in terms of either VC or IC. So I now know that. So now what I got to do here is that I got to connect. I got to connect these guys here. So now I got to connect VC and IC. So it doesn't make any sense to use a KVL loop that includes the 2IX, because the voltage across the 2IX should be the same as the voltage across the 12 ohm. So what I'm going to do here is that I'm going to apply a KVL around the outside loop. So apply a KVL loop around the outside. And because IX is through the 12 ohm resistor, note that I can rewrite IX from the DC condition. So now here I go. So KVL tells me I'm going to go towards the left here or to the right. So I'm going to get minus 8e to the minus 5. Then I'm going to get plus VC. Now note, let me be careful here. Look at the polarity of that 12 ohm resistor. Then I'm going to get my VC, which will be positive VC. And then I'm going to get positive 12IX. And that has to equal to 0. But IX is going to be what? 1/3 IC. from my DC condition here. So I'm going to plug this guy back into here, and this is what I'm going to get here. So what you're seeing here is that I'm going to get VC plus 12 over 3 IC must be 8 e to the minus 5t. Look how I connected them now. Now I got them connected, and now I got to come in and use my capacitor equation. So then IC should be the cap value, which is 136, times VC dt. So now I got to plug that guy in. So if I plug this guy in, I'm going to get what? I'm going to get 12.3 times 136 dV dt plus VC. And that's going to be 8 e to the minus 5t. So let's clean this up. So I'm going to get 12 and 36. That's going to give me, of course, a third. So I got a third and a third. That gives me 9. So now I'm going to multiply everything by 9. And so finally, I get this guy into proper form, which then reads VC equals to 72 e to the minus 5t. And so now I have my first order equation. Let's check this thing. Okay, let's do a simple check. So let's check IL at infinity. So we know that IL at infinity has to be a constant. So if I plug, so what I'm going to do now is that now sub this into first order equation. So I'm going to get VC at infinity dt plus 9 VC at infinity. And we can see here that, of course, that has to be 0 plus 9 VC at infinity. And this has to be what? 72 times e to the minus infinity, which is, of course, 0. This tells us that VC at infinity should be 0. That's what the mathematical equation. But wait a minute. If we come back up here, we already said that at VC at infinity, it should be 0. So check this out. Our first check is good on the first order equation. So we should be pleased, but not too pleased, because that doesn't mean that you derived it correctly. It just means that you did the first check. So let's go write this guy out. So now what I want to do here is that I want to go to step 2. And what do I got to do? I got to determine the general response, right? And solve for the forcing constants. Okay, so let's go look at that. So when I look at this thing, I start off with my first order equation. What I'm seeing here is that I'm seeing the following thing. The first thing that I see here is that I have what? I only have one term. That tells me I only have one constant. In this case, I'll just call it B, since there's only one. This guy over here is telling me that this is the 1 over tau value, which is 9. Okay, this immediately tells me that this is 9. So what this tells me here is that then our general response here should be VC of t should be A e to the minus 9t, and then my force response should be exactly functional form as the right-hand side of this differential equation, which then gives me B e to the minus 5t. That's what this guy's telling me right there, right? this is my general response right here. So my job here is to go solve for the forcing constants. And in this case, I got to solve for B. So now I need to determine the forcing constant B by subbing into first order equation. Let's do that. So here's my first order equation. So it's got to be what? V force plus 9V force. And then let's look at the forcing term. It's got to be B e to the minus 5t. So if I take the derivative of this guy, it's going to be minus 5b. And then if I plug that in, I'm going to get 9e to the 9b. And then the left side should look like this here. Now the right side, which is the force response or the effective source, then looks this way here. So of course you're seeing here is that then if I go calculate what B is here, it's got to be this here. So then my forcing constant is going to be what? 9 minus 5 will be 4. 4 into 72. Well, I know that 9 goes into it. Let's see. What is that? 72 divided by 4. I believe that's 18. Okay. Right? Yeah, it's 18. So I now have my forcing constant. So now my general solution looks like this here. So the general response is now going to be VC of t, which will be a e to the minus 9t plus 18e to the minus 5t. So now that was my goal of this section right here.
Carlos,
Yes.
what was the logic that told you that there's only one B term?
Because what you're finding here is that there's only one term right here. Now, if I go to the other one, look at the other one. When I came here, look at the source. The source here had two terms, 4 plus e to the minus 5t. So when I look at that equation here, you could see because I have two terms, I must have a B1 and a B2 here because there's two terms on the right. Here, there's only one term on the right, so I only have one forcing constant. Does that answer your question?
Yeah.
Okay, so now here I go, step 3. Let's go right through this guy here. So step 3 here then, what I'm going to do here is that I'm going to now solve the IC for VC of 0 minus and determine constant A. So let's go do that. So what I need to do here is that I need to go get that circuit. Now I have the circuit up here, so I'm just going to grab it. Okay. Oh, no, I don't. I don't have the circuit there. Here, let me bring this guy down here again. So let me go get that circuit here. So what I'm going to do here is that I'm grabbing it to bring it in. So here's my circuit. So what I see here is that I need the circuit for t equal to 0 minus. So at t equal to 0 minus, what we see here is that there's not this guy here. That's gone. So then I look at the rest of the circuit here. So you can see here is that my circuit really looks like this. I now have an open cap, and then I have this 3 ohm and this source right here. So here's my 38.5 volts. I have my 3 ohm. I have my 12 ohm. This is my 2IX. Then, of course, I now have my IX going this way, and I'm looking for this guy now. Okay, so let's go look at this thing. So the first thing that I got to do here is that there's lots of ways that you can do this. I think the fastest way to do this here is that I would probably consider doing a source transformation here. So if I do a source transformation, then all elements are going to be parallel. And if they're all parallel, I can add the two current sources, and then I'm going to get a nice simple circuit that I could do here. So let's do that. Let's do a source transformation. Now, I'm going to have to multiply these guys. So if I take, so let me do this here. So I can't do this in my head. What's 38 divided by this guy here? And I get a value of 12. I get 12.83 amps. Okay. So if I do that, look what I'm going to get. I'm going to get, I have a 12. I have a current source. I have my open. So now I have my 3 ohm. And now with my transformation, I now have a current source that looks like this. So it'd be 12.83 amps. Here's my 12. Here's my 2IX. Note that I can add the sources here. So if I add the sources, here's what I'm going to see. I now have a dependent source that has two terms. So it should be 12.83 plus 2IX. Right? This is what I'm seeing here. And let's be a little bit careful with this current here. Even though I'm drawing the current like this, it's also the current IX going in that direction here. So what I'm seeing here is that then I have two resistors. So I can't combine the 12 and the 3. I have to keep them separated because our condition for the 12 is that I need to see that IX right there. So then what do I have? I have another resistor, which is our 3 ohm. And note that the node voltage in this case, you could imagine here that I'm going to make this my ground. So you could see that here's my ground right here. And then up here, I have my voltage VC. So then this tells me that this is VC of 0 minus here. So I just got to get that voltage across any of the resistors, right? So what I'm seeing here is that I got to be a little bit careful here because that voltage has a polarity of plus and minus here. You could see that that IX is going from the negative to the positive. So if I look at the voltage of the cap here, I could see here is that if I calculate the voltage, I could calculate this any way I want here, but it seems like the easiest way to do this is that I'm just going to think about Ohm's law. So if I look at Ohm's law, I could see that the voltage across the 12 ohm should be the voltage across the cap. But look at the polarity. They're opposite. So it should be minus 12 IX. So this is how I got to get that initial condition right here. So let's go and apply it. So what I'm going to do here is that note this does not have a cap that's changing with time. So I could use simple circuits to actually do this. If you really want to get extreme, you could use node or mesh, whatever you want to do. I'm just going to use CDR, right? Because this is a regular circuit here. So I'm going to use CDR to get IX. So here I go. It's the opposite resistor. So if I want the current to cross the 12 ohm, it's got to be the opposite resistor divided by the sum of those two times the source. But wait a minute. What's the source? The source in this case has to be 12.83 plus 2IX. But remember, this is also IX right here. Oh, with the minus sign, right? There's a minus sign there. So I'm going to be careful. I don't want to do a double minus sign, right? I don't want to do a double minus sign. So what I'm going to do here is that I'm not going to choose the minus sign here. I'm going to keep my minus sign over here. I got to be careful. No two minus signs. So I'm not going to put a minus sign in here. So now I just got to go solve this thing. So if I solve this, I'm going to go to my notes. I'm not going to try to do this mathematically. So now I need to solve for IX. So if I get this for IX, right, solving this algebra equation, I get a value of 4.28 amps. Now that I got that, here's my initial condition. So then VC of 0 minus is then going to be minus 12 times 4.28 volts. And the value that I get here is going to be minus 51.3 volts, which is the same as V plus. We care about V plus, not about 0 minus, but 0 plus. So now I then have to apply this to our general response. So now I'm going to apply initial condition to general response to determine A. So if I do that, here's what we know. We know that VC at 0 plus, this guy is minus 51.3. And then I have to use our equation up here, which is this guy. So I'm going to get A e to the 0. So I'm going to get A e to the 0. And then I have the second one, which is plus 18 e to the 0. So now solving for A of course is then going to be minus 51.3 minus 18, which 1 plus 18 is 19. So this should give me, oops, I forgot the minus sign, minus 69.3 volts for A. So now I got everything about my solution. So here we go. What we're going to do here is that the complete response is then VC of t. I'm going to get minus 69.3 e to the, what is that? Minus 5t, I believe. Nope. That's not right. What's A? I got to go back and look. It is that. So that's 9 plus 18. And that's going to be 18 e to the minus 5t. And you know what? I just looked at this thing. It's not 5t, it's 9t. So there's our complete response right here. So what does this look like? What's the plot of this guy? Well, since VC of 0 minus and VC of 0 plus is continuous, that implies no discontinuities. It should be a smooth curve. And so when I go and I look at this guy, what am I actually seeing here? Well, for starters here, what we should be seeing is that we should be seeing something that starts where? Well, when I look at this guy, I'm seeing this here.
Carlos, when you say smooth curve, you don't necessarily mean differentiable.
Well, do you mean differentiable by that there's a slope value throughout this whole thing? The slope could be changing, but there's no discontinuity jumps, because if I take a derivative of this thing, it should be a smooth curve.
Like when t is equal to 0.
Well, let's
So there's
let's plot this and let's see. You're right. At t equal to 0, there's a kink in that.
Yeah, there's a
But
kink.
we don't typically care about what happens before. We only care about 0 plus.
That's fine. I just think smooth is misleading.
Okay, so we already calculated, look at this. We got this guy right here. So we know where it starts. So we know that it's got to start right here. So it comes in, and if I look at this guy, it's got to be VC of 0 minus has to be minus 51.3, oops, has to be 51.3 volts. So if I look at this guy, it's then has to go to V infinity, and we already said that VC at infinity has to be 0. And look at the solutions. They're all exponential decays. I would then expect here that this guy is then going to come in and do this type of thing. So if I look at VC, I'm seeing a plot that looks like a charging cap. So is this a charging cap? No, it's a decaying cap, because we saw that it had some voltage, but we got to be careful here because voltage is a constant. So it actually, in some sense, charges up, I guess, because a negative 51 is smaller than 0. But we typically don't interpret it that way. We just see that it's going to discharge to 0 here. So now the question is, how long does this thing roughly take to do this here? Well, if I look at this thing, God, this is a much harder question to really answer here. But I mean, the term that's really going to determine how long this thing is going to charge to, it's got to be this e to the minus 5 tau. So if I look at this thing, so the dominant time term is e to the minus 5t. So if I'm looking at tau, 1 over tau is really 5. So that tells us that tau is going to be 0.2 seconds. Now note that 9 has to affect the time. So if we had no e to the minus 9t term, then this implies that 5 tau is then going to be 5 times 0.2, which would be about 1 second. But the problem is that negative 9t term is there. So I would expect then, that that our 5 tau has to be less than 1 second. Now, if I was to be silly here, because I don't know how to estimate this without doing an actual calculation, I would say that that looks like about minus 10. That looks like about minus 5, which I can't do that. So I'll say that 5 tau is probably going to be in the ballpark of about 0.5 seconds. and let's just humor me for the moment. I think it's way more complicated than this because these are non-linear equations. My whole point is just to give you a sense of what I'm thinking about, that this thing should reach roughly, when this thing reaches 99.3% of discharging, should then be happening at a time of 5 tau, which I am giving a very rough estimate of half a second. I know it's got to be less than 1 second. So I'm just saying that it's half a second. Could it be less? Absolutely. Could it be a little bit more? I don't think so, but probably. So it's a really, really rough thing. The way to do that here is to plot it. And unfortunately, I did not plot it. Oh, actually, I did plot it because it's in my lecture notes.
You have a question in the chat?
I plotted the inductor time. Did I do the inductor? Oh, I didn't do it. Oh, I don't have time to plot that thing. Yeah, so if I had time, I would have gone in and plotted this thing. So I don't know what this plot is. So my apologies for that. Well, guess what? I am done with this chapter. So that means on Monday, we have a quiz. You're going to get 2 questions. One for a constant source and one for a time-dependent source. The time-dependent source is extremely important because when we move on to the next chapter for second-order differential equations, you're going to see that the deriving of the equations in the next chapter is a game changer. It really is something quite different. And there's no way in hell you ever talked about this in Math 7. You'll see what I mean. So, any questions before I sign off? So I think I'm giving you an extra 20 minutes on the quiz. So I think you have I typically give you an hour. So I'm going to give you, I think I set it 80 minutes for the quiz to do 2 problems. And that 80 minutes may not be enough time. You want to be...
It just took us 80 minutes to do examples that you'd already done.
Yeah,
So,
but
yeah,
if
that
I
might-
was...
that
Yeah,
might
but...
be the case.
Yeah, but I'll tell you one thing. I would not be writing as much as I write if I was solving this problem. You're probably not going to write all the words and when you write that. Well, I know you do because I grade your quizzes. You guys don't write that way. Your ass is just trying to write an answer as quickly as you can. So yeah, that's not going to be an issue, Isaac.
We could just round it up to an even 2 hours and call it good, though.
Yeah, thanks for the suggestion, Tim.
Well, you're welcome anytime.
Noted and
How do I
ignored.
say this? Nope. Okay. Hey, I want to let you know that on Thursday, I will not be in my PLC hours for just about 15 minutes. It's my last commitment for the college this semester as far as committee work. So I apologize, but I expect to see a lot of you during the office hours, especially on Monday. I'm expecting it's going to be jam-packed. Don't wait till the last minute to do these. Remember what some of these people tell me. If you start a couple days beforehand, you may not finish it. I know that for a fact next chapter.
Are there any circuits resources on Sundays?
Not that I'm aware of. Is the STEM Center? I know that Paul's around.
Saturday only.
Saturday only?
Yeah.
Yeah, I wish I had more. I'm out of town this weekend, so. Hey, I got to give some equipment out. By the way, Josh Booth figured out how to get the function generator to work on the oscilloscope. You punch them into the side right here, and they actually work. So
Maybe sometimes.
yeah, actually, mine worked every single time. I tried 2 others, and they worked every time
Every time that you put them into the side.
into the side, and because I have 2 other digital oscilloscopes, and they both work when I punch them in there. So I've tried it on 3, and they all work on 3.
Incredible.
Incredible.
What's the difference between the ports?
No idea.
What does the manual say on this matter?
Shit. Well, I know
One of them's on the
their
side.
website was misleading. I'll tell you that much. Hey, I got to get out of here. I got to get to Physics 4A lab. Man, peace. Enjoy the long weekend. Okay.
You will. Thanks, Carlos.
You bet.